Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hello students, wish you all a very happy new year. Today we are going to start a new chapter, the surface chemistry. And the surface chemistry will study mostly about the phenomena which occur at the surfaces or interfaces. And we know what are the surfaces, these things we have seen also in solid state chemistry. And interfaces are where two surfaces meet, or two different surfaces meet, or maybe that when two phases meet each other, we call such places are interfaces. And what are the interfaces we have seen within electrochemistry as well. So the subject of surface chemistry finds many applications in industry, analytical work, and daily life situations. Particularly, we'll see the heterogeneous catalysis. It's a very much celebrated branch of catalysis, and particularly if you know the Ziegler-Natta catalysis, the formation of different types of polythenes. All this polymerization happens at surfaces mostly in the form of heterogeneous catalysis. And where MgCl2 magnesium chloride surface is used, titanium chloride molecule goes on the magnesium from some particular surface of magnesium chloride, and then the polymerization of polythene happens. And we all know the importance of the polythene in our life and how it has changed the life, human life completely on the earth. And this is where we have actually a new kind of reaction that we have done. We have synthesized certain molecule or certain kind of material which was never been there in the on the earth, or it was never known for such molecules or such substances, such materials were never known for human beings, and it was not synthesized by similar substances, were not synthesized by the nature. So in this unit, we will be studying some important features of surface chemistry, such as adsorption, catalysis, and colloids, including emulsion and gel. We will study about them. And you can see in this figure, particularly in this picture, what we are seeing, this is a surface, and then this surface water molecules is being absorbed. And after the adsorption, what you see, this O red color ball is oxygen atom, and this whitish color ball is hydrogen atom, and this hydrogen is getting separated. Water is being molecule is splitted here. So it is splitted into the form of H plus and OH minus. So such reactions also happen at the surface. So splitting of water molecule, and then know the importance of water molecule splitting in the catalysis and other areas. So in the interfaces of surfaces is represented by separating the bulk phases by a hyphen or a slash, and this slash we know this is slash, this kind of thing we have also seen in the representation of uh, cell reaction. We use certain slash, or maybe the oblique lines we use there for the parallel oblique line. So we use separate bulk phases from the surfaces by hyphen or a slash. For example, interface between a solid and a gas may be represented by solid gas or solid this slash solid dash gas or solid slash gas, this representation. So there is a hyphen means solid and gas. Maybe this is the bulk phase and this will be on the surfaces, and so this maybe they may be separated. This is a representation of the adsorption. So due to complete miscibility, interface does not exist between the gases, and this is one point you should understand. Interface doesn't exist between the gases because all the gases they are in the same phase, and when they are all in the same phase, gaseous phase, they will mix with each other. I mean, they will mix with each other. There will be no surface, and so there will be no interface between gas molecules or two gases. The bulk phases that we come across in surface chemistry may be pure compound or solutions, and this is what bulk phase may be the pure compound or the solutions. And pure compound that we know the bulk solid can have the other than surfaces, all the major part of this solid will be the bulk, and the solutions we know solutions bulk and all the solvents bulk that we know. The interface is normally a few molecules thick, but its area depends on the size of the particle of the bulk phases. And when we talk about the interfaces, means where two surfaces meet, different types of surface, two phases actually mix, and so this interface of any substance will be only few molecule or few atoms thick, and this thickness will it also depends on, and its surface area will depend on the particles of the bulk presence, what are the particle size and other things, what that is there that forms the bulk depends on depending on that the surface area and other things depend. So many important chemical phenomena such as corrosion, electrode processes, example that we know, electrode processes particularly when you know the electrode reactions happening at the electrode, they all, of course, electrode, we know it helps, it does two work. One is to conduct electrons or to maybe the facilitate the transfer of electron from one area to the another area or one region to the another region, one can say. And then another is it provides surfaces where the electrode reactions can happen. So electrode processes in the when also this also happens at the surface where ions meet the electrons or the heterogeneous catalysis. Heterogeneous catalysis, the example we know the two types of catalysis when the catalyst, the different reactants or maybe the catalyst is in the different phase than the reactants, then we call such catalyst as heterogeneous catalyst. And the example that I have said for the Ziegler-Natta catalyst is MgCl2 surface. MgCl2 is actually in the solid phase, and then we see the titanium, the polyethylene formation, that is a gas in the gaseous form, and many other molecules that we use for the catalysis that in different phases. So that is an example of heterogeneous catalysis. However, homogeneous Ziegler-Natta polymerization, some examples are also there, although that is not industrially not that mm, efficient, but the process is olefin polymerization is a homogeneous Ziegler-Natta catalysis is also known. Some catalysts, homogeneous catalysts also do polymerization, although their efficiency is less than the heterogeneous catalyst. So the heterogeneous catalysis dissolution, that we also know the dissolution and crystallization occurs at interfaces. The dissolution of a crystal into a solvent, or the crystallization when the crystallization happens at solid particles, the certain solid particles, new particles they get deposited. So that this is how the crystallization happens. They all happen at the interfaces. So to accomplish surface studies meticulously, it becomes imperative to have a really clean surfaces. This is one thing, to have a particular type of reaction or to accomplish a particular type of reaction or to have a meticulous study about the absorption and this surface reactions. It is very important to have the surfaces very clean. And when you talk about the absorption of gases on the surfaces, particularly you have to have these gases, particularly very high vacuum is required because oxygen and nitrogen, these gases has certain affinity with all the solid surfaces. And if the high amount of the high vacuum is not, high order of vacuum is not created, means 10 to it's created into the order of 10 to the power minus 8 to 10 to the power minus 9 Pascal, then some of the gases of atmospheric gases will always be absorbed on the surfaces, and so that's what the different kind of bomb mixing and that clean reaction and mechanism understanding will not happen. So usually surface reactions when we do, we actually use very low pressure and that we do under very high order of vacuum. So it is not possible to obtain ultra clean surfaces of the metals, and particularly metal surfaces when we are talking about. Metal surfaces have certain affinity with oxygen, particularly they easily form oxide. They also have affinity with the nitrogen. They form nitride or similar kind of things. Although their affinity with nitrogen is not very high, but their affinity with oxygen is high, so it is difficult to obtain clean metal surfaces at normal pressure or even at low pressure until unless a higher order of vacuum is not created. Solid materials with such clean surfaces needs to be stored in vacuum, otherwise these will be covered by molecules of major components of air, namely dioxygen and dinitrogen. It means when the solid surfaces with such a clean such a clean surface, solid surfaces are created once at a very high order of vacuum, then such surface should be stored in vacuum only. Otherwise, once you, after cleaning, you bring it back to the normal pressure and in the contact of atmosphere, the dioxygen and dinitrogen and some other gases of the atmosphere will get absorbed at those surfaces. So whenever we are talking about adsorb, those gases will be absorbed. So what is the adsorption? So the adsorption, when we are talking about adsorption, means the solid surfaces we are taking and some other materials, maybe the gas molecules or some other molecules. When they come and get clinged to the surfaces of the solids, they cling there, they stuck there, and then this process we called, and they are only they get accumulated on the surfaces, then this process is called as adsorption. The surface of a solid has the tendency to attract and retain the molecules of the phase with which it comes in contact. So with whatever phase it comes in contact with the solid surfaces, it retains some of the molecules of that, particularly the other molecules with which the solid surfaces come in contact with is liquid or gas. Then some molecules from the liquid and solid phases, they come and they will get attracted by the atoms or the molecules, the portion of the solid that is exposed at the surfaces. It gets attracted by that, and so they get accumulated on that portion, and these molecules remain only at the surface and then do not get deeper into the bulk. And so this, when other they accumulate only at the surface and they do not go into the bulk, this process is known as adsorption. So the accumulation of molecular species at the surface rather than in bulk of a solid or liquid is termed as adsorption. So at the surface, accumulation of molecular species when it comes and of a solid liquid is termed as adsorption. I'll read that again. The accumulation of molecular species at the surface rather than in bulk of a solid or a liquid is termed as adsorption. And this adsorption may also happen at the surface of the liquid, and it will in fact definitely happen at the surfaces of the solid, because when we are talking at the surfaces, we talk about the surfaces of solid or the liquids. They only have the surfaces. So the molecular species or substance which concentrate or accumulate at the surface is termed as adsorbate. So whatever the species or chemical species or the molecular species which get absorbed at the surfaces or which get accumulated at the surfaces, which get clinged to the surfaces are called adsorbate, and the material on the surface of which the adsorption takes place or in which this accumulation of the chemical species take place on the surfaces of whatever the material, that material is called adsorbent. So the molecular species or substance which concentrates or accumulates at the surface is termed as adsorbate, and the material on the surface of which the adsorption takes place is called adsorbent. Adsorption is surface phenomena. That is why is what we have seen. So adsorption is what? Surface phenomena. It means to increase the surface area of a substance, adsorption, the extent of adsorption should increase. And that is why when a large solid material, when it is divided into fine particles, so on dividing a large volume of a material, when you divide it into the small fine particles, we know the surface area increases. For example, if you have a ball, a large ball of 1 meter cube, metal ball of 1 meter cube volume, then you can break this into thousand smaller balls, and you can just similarly volume one, not volume, what the surface, one can assume that a ball of 1 meter radius, a spherical ball of 1 meter radius, then we can find out the volume. And if you divide this entire volume into thousand smaller balls, so all the thousand smaller balls have their volume accumulated sum together will be equal to the volume of the larger ball. And with that, when you ever you can find out the radius of the smaller balls, each smaller ball, and when you look at after the radius, you can find out the surface area and sum of the surface area of all the thousand balls, smaller balls. And when you compare this with the surface area of the larger balls, you know how one can get the surface area of a sphere. And when you see that the surface area of the thousand smaller balls which were created from one large ball is greater than the surface area of the larger ball. And this means if you divide a solid particle material, a larger material into a smaller fine particles, the surface area increases. So so solid in finally divided state, have large surface area, charcoal, silica gels, alumina gel, clay, colloids, metals, etc. In finally divided states act as good adsorbents. Why? Because when the finally divided states of what the surface area is more, and since adsorption is the surface phenomena, so with the surface area increase in the surface area, adsorption also increase, and so they become the finally divided particles, and divided particles they act as a good adsorbent. So what we see, this is the larger surface and this is the interface, and where this bulk, the phase is actually at the surface meets with the some other phase. And what happens, this is the adsorbent, some molecule get adsorbed, they get accumulated at the surface of this larger ball, and maybe this is smaller balls that we see. So this material, this process of accumulation of this smaller balls over the larger balls is called adsorption, and the smaller balls will get absorbed or we get accumulated over the larger ball or the surface are called adsorbate, and the material on the which surface the adsorption or the accumulation of adsorbate take place is the it's called the adsorbent. So this is called adsorbent, and this thing we have seen now. So some noted examples of adsorption one should let's see what are the some noted examples. So if gases like oxygen, dioxygen, dihydrogen, carbon monoxide, dichlorine or diatomic chlorine, ammonia, sulfur dioxide is taken in a closed vessel, when any of these gases are taken in a closed vessel containing powdered charcoal, and if that vessel contains powdered charcoal, the pressure of these gases in the enclosed vessel decreases. So after some times what we observe is the pressure of in all these gases decreases after certain time. And what other thing that we see on the gas molecules, these gas molecules they get concentrated on the surface of the charcoal. So their concentration, their accumulation increases on the surfaces of the charcoal, and this by the process of adsorption. And this process we know such examples is adsorption. Anyway, the this pressure, vapor pressure, their pressure decreases. It means some of the molecules are now not in the gaseous state. They had gone somewhere else, and where do they go? They have gone and they get accumulated to the surface of the charcoal. So they have certain affinities with the surfaces of the charcoal. So another example is in a solution of an organic dye. So if take an organic dye, take a solution, for example, take methylene blue. When animal charcoal is added in that solution, and the solution is well shaken, and when you shake that solution, the filtrate turns colorless. So the solution part, the filtrate part, it turns colorless. Initially, it contained dye, so it has certain color. But after mixing the charcoal, animal charcoal, and then shaking the solution, what we see, the filtrate the solution part, the liquid part becomes colorless. And why it becomes colorless? Because that dye get got absorbed on the surface of charcoal, and because of that adsorption or the accumulation of a dye on the surface of charcoal, now dye is not there into the solution form, and thus this filtrate turns colorless. The aqueous solution of raw sugar. Whenever we know the raw sugar, the cleaning of the raw sugar, initially its color is like grayish color. They have certain brown color, and when we pass this aqueous solution of raw sugar over beds of animal charcoal, when we pass that raw sugar over beds of animal charcoal, this aqueous solution of raw sugar become colorless, as the colorless substance of that raw sugar are absorbed by the charcoal. Whatever the coloring substance was there in the raw sugar, that got absorbed on the animal charcoal, on the surface of animal charcoal, and later on the sugar becomes white, and this is what the sugar that we use. The air becomes dry in the presence of silica gel. This is another example. When you take silica gel, the air becomes dry, and because the water molecules get adsorbed on the surface of the gel, and silica gel, this kind of thing, some silica particles we also use the boxes and so inside bags. So the air becomes dry in the presence of silica gel. And why it becomes dry? Because water molecules here also contains water vapor. Some molecules of water are in the form of moisture, and those molecules of water they get absorbed on the surface of silica gel, and so air becomes dry. It is clear from these examples that solid surfaces can hold the gas or liquid molecules by virtue of adsorption, and this is what we have seen. So by the virtue and by the phenomena of adsorption, the solid surfaces can hold gas or liquid molecules at the surface only, no, and those molecules do not go, they do not percolate down into the bulk. The process of removing an adsorbed substance from a surface. So once the substance gets adsorbed, then what happens? One can also remove that substance, adsorbed substance from the surface. So that process, the reverse process is called, the reverse process of adsorption is called desorption. So the reverse or the reversible process of adsorption is desorption. It means removal of the adsorbed substance from surface. The surface is called desorption. Now there is another term that we use that we call absorption. So absorption, on the other hand, what we know, it goes deeper, involving entire volume of the absorbent. So absorption is what the entire volume of absorbent is used. So for like similar to absorption and adsorbent, one can also use the term absorbent. So the material which absorbs certain molecules or some other substance is called absorbent, and something which get absorbed, it is AB. So absorb is called absorbate. So absorption, what happens? Absorption happens to the entire volume of absorbent. And usually absorption of some solvent happens, like absorption of water may happen. And the water is particularly absorbed by certain metallic crystals or the ionic compounds, and that water molecule that we call water of absorption, water of crystallization. So those molecules or the water molecules or solvent molecules of absorbate, they go and fill the pores or holes in the substance of the substance we call as absorbent. So absorption goes deeper, involving the entire volume of absorbent. So absorption is the filling of pores or holes in a substance. Let's see distinction between absorption and absorption. Just 1 minute. I don't know from where the noise is coming. क्लास ले रहा हूँ मतलब कम कर देंगे बोले कम कर दो क्लास ले रहा हूँ 1 घंटे बाद फोन कर लो Okay, so I'm sorry. Coming from sound. So, so let's see the distinction between or the differences between adsorption and absorption. So in adsorption, what we see, the substance is concentrated only at the surface and does not penetrate through the surface to the bulk. So the substance is only accumulated or concentrated over the surface and it does not go or percolated down to the bulk of the adsorbent. However, in adsorption, what we see, substance is uniformly distributed throughout the bulk of the solid. For example, when a chalk stick is dipped in the ink, to see the chalk stick is dipped into the ink, what we see the surface is the coloring agent of the ink. It gets absorbed on the surface of this chalk stick. However, the solvent, it goes inside the bulk, and so this solvent molecule it get absorbed and the coloring agent of that ink it adsorbed. So the surface retains the color of the ink, the coloring agent, due to adsorption of the colored molecules. However, the solvent of the ink goes deeper into the stick due to absorption, and this process we call the solvent goes inside the bulk because of the absorption. And on breaking the chalk stick, what we see, it is found to be white from inside. So the chalk stick is found to be white from inside. It simply means that the coloring agent has not percolated down, has not gone down into the bulk of that stick. However, you see, even when you break it, you see that even the inner part has the presence of the water molecule, the liquid, the solvent. So it gets weighted. So that's why it means the water molecule has gone down, it has gone into the bulk, but the surface, the coloring agent has not gone into the bulk, and that is why from the inside that the broken part, when you see, it is still white, though it is wet. The distinction can also be made between adsorption and absorption by taking an example of water vapor. So, I'm sorry. When we take the example of water vapor, what we see, as I said, water molecules may be absorbed by the crystals of certain ionic compounds because those water molecules inside the crystal, actually these water molecules helps in the crystallization as well to form a better crystal. So that water molecules is called as water of crystallization. So when you take anhydrous calcium chloride, this anhydrous calcium chloride can absorb water vapor. So it will absorb water vapor. So it will absorb water vapor will go inside the crystal, and it will also help in the crystallization. And but this water molecules, when you use silica gel, this water vapor will only be attached at the surfaces of the silica gel through the hydrogen bonding. So from the weak bonding, the hydrogen bonding, it will be there on the surfaces through weak bonding. However, the water molecules which go inside the crystal shell with the water of crystallization, they may form a coordinate bond or maybe the covalent bond with the metal ion. So in other words, in adsorption, the concentration of the adsorbate increases only at the surface of the adsorbent, while in absorption, the concentration of absorbate, okay, is uniform throughout the bulk of the solid. Both adsorption and absorption can take place simultaneously as well. So both adsorption and absorption may take place simultaneously, as we have seen the example of the chalk stick when it is dipped inside the ink. Both the processes are happening simultaneously, and such processes are called sorption. So this term we use sorption. So this adsorption and absorption may take place simultaneously in some cases, and this process we call as sorption. So types of adsorption, let us see. So there are particularly two types of adsorption that we study about: physisorption and chemisorption. And from the terms itself, you understand physisorption is just a physical adsorption. And physical adsorption means it will, the adsorption will be because of the weak interaction, weak non-covalent interactions, and that interaction may be van der Waals type or maybe hydrogen bonding, as we see in the case of water vapor get adsorbed at the silica gel. We see that interaction is the hydrogen bonding. So the physisorption is mostly because of the physical adsorption. Physisorption is the physical adsorption, and chemisorption is the chemical adsorption. And chemical adsorption with chemisorption means there is some type of certain chemical reaction that happens. So a new type of bond formation happens between adsorbent and adsorbate. So adsorbate is the material which is accumulated, and adsorbent is what? The material on the surface of which adsorption is taking place. So that is adsorbent. So chemical bond formation happens between adsorbent and adsorbate, and such adsorption and such accumulation of adsorbate over the adsorbent is called chemical adsorption or chemisorption. And so what we see, the chemisorption, the formation of a new bond, and formation of new bond happens with the breaking or the cleavage of the certain old bonds. And whenever you are trying to break certain old bonds, means what? It means you need to provide activation energy, and that activation energy to make that reaction and that process happens get facilitated. You need to provide certain activation energy, and that is why that sorption, chemisorption, is also called chemi adsorption or activated adsorption. They are also called chemisorption is also called activated adsorption. So there are mainly two types of absorption of gases on solids, particularly when we talk about the absorption of gases on the solids, and not only the gases, some other materials may also happen a similar thing. So if accumulation of a gas on the surface of a solid occurs on account of weak van der Waals forces, and means the accumulation of gas happens because of the weak van der Waals forces, the adsorption is termed as physical adsorption or physisorption, which I have already explained. When the gas molecules or atoms are held to the solid surfaces by chemical bonds, the adsorption is termed as chemical adsorption or chemisorption, and the chemical bonds may be covalent or ionic in nature. And this chemical bond that which actually is formed between adsorbent and absorbate may be the ionic bond or the covalent bond. The chemical option involves a high energy of activation, and why it requires high energy of activation or involve high energy of activation, because to make a new bond some old bonds has to be broken, because the valency or the covalency or the ionic valency of the substance which is at the surface must be maintained, and that valency, to maintain that valency, and if you are forming a new bond, the old bonds, some older bonds must be broken, and to break that bonds a high energy of activation is required. Therefore chemisorption is often referred to as a activated adsorption. Sometimes these two processes occur simultaneously, means the physisorption and chemisorption both happen simultaneously, and is not easy to ascertain the type of adsorption, and those cases it becomes very difficult to ascertain what type of adsorption is taking place, whether it is chemisorption or physisorption. A physical adsorption at low temperature may pass into chemisorption at higher temperature, while at low temperature the energy of activation cannot be achieved, one cannot get, because that much kinetic energy is not there into the molecules. And when you increase, so only physisorption will take place at lower temperature. But when you increase the temperature, the gas molecules which were there, or the molecules may their kinetic energy will increase. So a collision may become effective collision, and so the chemisorption will take place, formation of new bond may take place, and so the activation energy can be achieved because of the increase in temperature. And that energy increase in temperature that we know because of increase in kinetic energy. So for example, dihydrogen is first adsorbed on nickel by van der Waals forces. So dihydrogen initially on the nickel surface it is adsorbed because of the physisorption, and the interaction between dihydrogen and the nickel is only the weak van der Waals forces. However, molecules of hydrogen then dissociate to form hydrogen atoms which are held on the surface by chemisorption, and then after certain time what we see, because of the collision between hydrogen molecule and the nickel surface, what we see, some collision will have the energy equals to the threshold energy, and these things we have seen in chemical kinetics, so that it can actually cross the barrier and the chemisorption will take place, and so this hydrogen molecule will be broken into hydrogen atoms. So the older bonds that were there between two hydrogen atoms will be broken, and a new type of bond between nickel and hydrogen atoms will be formed. So nickel hydride will be formed at the surfaces, and this process we call the activation of hydrogen molecule, or the activation of hydrogen, because hydrogen bond is activated, it is broken, it is elongated initially and then finally broken, so the hydrogen will come into the atomic form. This we also call, as you know, activation of hydrogen. Let's see characteristics of physisorption. So there are some characteristics of physisorption. The first is lack of specificity. So physisorption do not have any, doesn't have any specificity, because there is a van der Waals interaction, and van der Waals interactions are universal interactions. It can happen between any two particles. It doesn't depend. It only depends on the surface area of two particles. It may not depend on some other things. Although the extent of this interactions may slightly vary, but there will be certain interaction, van der Waals interaction, or the dispersion interaction between any two particles, any two chemical species. And so one can say the physisorption, if it is happening, it will not recognize between two molecules. Although the extent of adsorption may vary depending on the surface area or the interaction and also size, many other things. But this kind of absorption will happen between for any molecule, so there is no specificity. So lack of specificity, the physics option has, it means a given surface of an adsorbent does not show any preference for a particular gas as the van der Waals forces are universal. So nature of adsorbate. So nature of adsorbate, however, may affect the adsorption or the extent of adsorption, and this we call the amount of gas absorbed by the solid depends on the nature of gas. And this nature of gas, because there are two interactions that may happen at the surface edge. One is between the surface and the adsorbate molecules, I mean the adsorbent surface and the molecules at the adsorbate surface and the adsorbate molecule, and the another interaction is when one molecule of adsorbate is already adsorbed and another molecule of adsorbate comes near this molecule, so there might be another interaction between the adsorbate and adsorbate molecule. And this interaction and this kind of interaction, if you see interaction between two molecules, it actually causes the change in the physical states of the material, because the interaction between these two particles actually determines what will be the melting boiling point of that material and also the thermal energy that you know that work. But the measure, the determining factor is the interaction between the two particles or two molecules, and if that interaction is greater than the thermal energy, we know this kind of things we are seeing. I don't want to go into that thing. So what that is what it means, that the physical state or the liquefiable gases. So in general, what we see, the gases with higher critical temperature have they are easily liquefiable, and easily liquefiable, it means what, their melting and boiling point will be higher than the gases which critical temperature is lower. So in general, easily liquefiable gases, and what are the easily liquefiable gases? When their interaction between those gas molecules will be higher, so they will be easily liquefiable. So in general, easily liquefiable gases, that is with the higher critical temperature. So the gases with higher critical temperatures are easily liquefiable, and also the gases with higher molecular interactions are easily liquefiable, are readily adsorbed as van der Waals forces are stronger near the critical temperature. So the van der Waals forces between these molecules will also be stronger and more, and when these gases, because these gases are getting accumulated at the surfaces, and so that property is kind of the liquefaction of the gas, because gas molecules initially were in the gaseous form at the larger distances, but now when they come on the at the surfaces, they become closer to each other as if they are in the liquid phase. So thus 1 gram, if you look at the example, 1 gram of activated charcoal absorbs more surface dioxide. On the sulfur dioxide, its critical temperature is 630 Kelvin. Then the methane, which critical temperature is 190 Kelvin, and which is still more than 4.5 ml of dihydrogen, and that is the critical temperature is 33 Kelvin. So the what does it mean? The sulfur dioxide, 1 gram of activated charcoal absorbs more sulfur dioxide than the methane, and methane absorption of methane is more than the absorption of dihydrogen at the same surface, because dihydrogen, the critical temperature is lowest among three gases. So if the gas critical temperature of the gas is higher, so its absorption will be higher. So nature of adsorbate also affects the extent of physisorption. The physisorption will be more when the gas critical temperature is more. So enthalpy of adsorption, and then what we know, the physisorption is an exothermic process. Usually any adsorption is an exothermic process, because if you remember, I have said that there is interaction, attractive interaction between different molecules, and whenever there is attractive interaction, it means the kinetic potential energy of the system will go down, and because of that, some energy will be released, and that energy, released energy, means the process is exothermic. So physisorption is an exothermic process, but its enthalpy of adsorption is quite low. But since we know this physisorption, it involves very weak interaction, and so that is why enthalpy of adsorption will be quite low, and it ranges between 20 to 40 kilojoule per mole. So the enthalpy of adsorption, the physisorption is only, it ranges between 20 to 40 kilojoule per mole, because of the weak interactions that happens between adsorbent and adsorbate molecules. And that if the reason is given, this is because the attraction between gas molecules and the solid surface is only due to weak van der Waals forces. Now the fourth property is the physisorption is reversible in nature. And the physisorption is reversible in nature means that because this adsorption has either no barrier or very low barrier. And this barrier, smaller barriers are, which means they have almost barrier. This is almost barrierless process. And so physisorption of a gas by a solid is generally reversible. The solid plus gas, when we see, when it gets absorbed, the gas gets absorbed on the solid. This is how we see the interface. We show interface between gas molecules and the solid, and some heat is released, and this process can be reversed and go into the reverse direction. So the gas molecule, when you start with absorbed gas on the solid, and when you can see that this desorption will also take place in solid and gas molecules, and this process absorption and desorption, it also depends on the pressure of the gas. When the pressure of gas is high, what this is, the pressure of gas is high and leach arterial principle will be applied here, it will be valid here, and so what will happen, the reaction will go in the forward direction to decrease the volume, and it will go into the forward direction, so the adsorption, extent of adsorption will be more. When you decrease the pressure of the gas, the reverse reaction will happen, and so more and more gas molecules will be dissolved from the solid surface. So more of the gas is adsorbed when pressure is increased as the volume of the gas decreases on adsorption, and on adsorption with no gas molecules get closer, their volume decreases, and so this is according to Leach-Arterias principle, and the gas can be removed by decreasing pressure, and this gas can be removed by decreasing the pressure since the absorption process is exothermic, and what we have seen, this absorption process is exothermic. So when you increase the temperature, so desorption will take place. So physisorption will be reversed, and when you decrease the temperature, physisorption will go into the forward direction. So since the absorption process is exothermic, the physical absorption occurs readily at low temperature and decreases with increasing temperature, and this is also in accordance with the Leach-Arterias principle. And the surface area of adsorbent. And we know, we have seen earlier, surface area of adsorbent also affects the extent of adsorption, and that we see usually if the surface area of adsorbent increases, then the physisorption will, extent of adsorption will increase, and the extent of adsorption increases with the increase of surface area of the adsorbent. Thus finely divided metals and porous substances, and the porous substances will, which pores also have certain surfaces, and the finely divided particles, we know they also have higher surface area, and so they are good adsorbents. The porous surfaces or the finely divided particles are good adsorbents because they have, these adsorbents have high surface area. Now let's see the characteristics of chemisorption. So high specificity. So first is the high specific. Chemisorption is very specific. So chemisorption will happen only few materials get chemisorbed on a solid surfaces of a specific type. So it is specific. So suppose a metal surface of particular type you take, like maybe if you take MgCl2 surfaces, the metal is there. So not all the materials will get chemisorbed at MgCl2 surface. Only few materials will get chemisorb, and those materials will have certain affinity, higher affinity with the metal or the chloride that is there on the surface. So chemisorption is highly specific, and it will only occur if there is some possibility of chemical bonding between adsorbent and adsorbent. And it means, this is because if there is some possibility of chemical bond formation between adsorbent and adsorbate, then only this chemical adsorption will take place, and that is why the chemical adsorption or the chemisorption has higher specificity. And if you take the example, oxygen is adsorbed on metals by virtue of oxide formation, and oxygens get adsorbed in metals because on the metal surface oxygen turns into oxide, so metal oxide formation takes place, and that is a chemical bond formation takes place at the metal surfaces. And hydrogen is adsorbed by transition metals due to hydride formation, and the hydrogen also get adsorbed on the transition metal surfaces. For example, we have seen the example of the nickel earlier. So nickel is also a transition metal surface. And hydrogen get absorbed, can be absorbed at the metal surface because hydrogen is broken into atomic hydrogen because it means hydrogen turns into dihydrogen turns into the hydride. It means if there is a nickel hydrogen bond, hydrogen will definitely its electronegativity more higher than that of nickel, and so it will exist in the form of hydride. And the irreversibility, the chemical option are usually irreversible because this process has to in a barrier, and because of this barrier, the existence of barrier, presence of barrier, or the activation energy chemical option are usually irreversible. Because to have this reaction happens in reverse direction, you require a higher energy than the energy that you required for the activation to come to cross this activation barrier. You need even higher energy because in the forward direction some energy was released. This was also an exothermic process. Usually, so irreversibility chemical absorption involves compound formation, and it is therefore is usually irreversible in nature. Usually irreversible in nature. Chemical absorption usually means not. There might be some 10 exceptions. So chemical absorption is also an exothermic process, but the process is very slow at low temperatures. So what we know, the chemical absorption is exothermic process. I have seen, but this process is very slow at low temperatures because why at low temperatures the crossing of the activation energy and the molecules may not surpass the activation energy barrier. So at low temperatures, when the molecules have lower kinetic energy, their collisions will also have a lower kinetic, a lower in kinetic energy of the collision. So those collisions, the effective collision will be very few. When at the however at the higher temperature, the kinetic energy increases, and more molecules will have the potential to cross that activation barrier. So chemical absorption becomes faster at higher temperature because this high activation or energy of activation can be crossed at higher temperature. So like most chemical changes, absorption often increases with the rise of temperature. So this is what we know. Like other chemical changes, the chemical absorption often increases with rise in the temperature. So chemical processes also increases because the activation energy barrier rate increases because the rate constant increases with temperature. We know the rate constant relation with the temperature, the Arrhenius equation. So at high temperature, so physics option of a gas absorbed at low temperature may change into chemical option at a high temperature. And this is one thing that we have seen earlier as well. So physics option of a gas absorbed at low temperature. Why it was physics option at low temperature? Because chemical transformation may not happen. The new bonds may not be formed because old bonds cannot be broken at lower temperature because of the activation energy involved in this process. Or the activation energy barrier is already there for all the chemical changes. So the physics option which was at the low temperature may turn to chemical option at higher temperature because as you increase the temperature, kinetic energy of the molecules will increase or the absorbed molecules will increase and the energy after the collision, the energy will also be and the collision frequency will also increase with the temperature, and so what will happen? The chemical physics option will turn into a chemical option. So usually high pressure is also favorable for chemical option like other chemical transformations. So heavy absorption of a gas absorbed at low temperature may change into heavy absorption at high temperature, and it so this thing. Now the surface area like phase absorption, the surface area when surface area increases, the chemical absorption also increases. So like phase absorption, chemical absorption also increases with increase of surface area of the adsorbent. So once you increase the surface area of adsorbent, chemical absorption also increases because more and more molecules are now exposed of the adsorbent are now exposed for the chemical transformation at the surfaces with, when they come in contact with the adsorbate. The enthalpy of adsorption and enthalpy of chemisorption is usually high because we know chemical transformation. In the chemical transformation, if a new bond is the new favorable bond is formed in presence of in expense of old weaker bonds, then this chemisorption it will release higher energy, and so the chemisorption is associated with the higher energy enthalpy of absorption, and this enthalpy of chemisorption is high. So enthalpy of chemisorption is high, and it usually ranges between 80 kilojoule to 240 kilojoule per mole. So 80 kilojoule to 240 kilojoule per mole is the enthalpy of chemisorption, as it involves chemical bond formation, and chemical bond formation we know happens with the release of energy, so that energy will be higher. Let's now see the types of absorption we have seen, and let's see the differences between them. The physics option. The physics option, what we have seen, it involves the use of peak van der Waals forces by means of which gas molecules get absorbed on a solid surface. So chemisorption is what it involves chemical bond formation between the gas molecules and the adsorbent surface. How the molecules or the atoms that are present at the surface of the adsorbent. So physics option, then what we have seen, it is not specific in nature. So physical interactions, the van der Waals interactions may happen whether weaker or stronger between any two molecules. But the chemisorption, the chemical bond formation requires certain kind of property and certain affinity. Only certain molecules have certain affinity with the other type of atoms which are exposed or which are there at the surfaces of the solids. So it has the chemisorption is specific in nature. So physics often depends on the nature of gas, and by the nature of gas that we have seen, more easily liquefiable gases are absorbed readily. So if the gases are more easily liquefiable, they get more absorbed more readily, and this liquefiability because the interaction between gas molecules will also affect the absorption of the gas, the next coming gas molecules on a surface. However, chemisorption depends on the nature of gas. It also depends on the nature of gas, and here the nature of gas is the chemical nature of gas and not on the physical interactions and the weak interactions. So gases which can react with adsorbent, so chemisorption. Only gases which can react chemically with the adsorbent molecule, they show chemisorption, not all the gases. And so it is also a specific in nature. Now, the physics option is reversible in nature, that we have seen. Physics option can easily be reversed just by modulating the pressure, and that is why at higher pressure physics option the extent of absorption will be more. At lower pressure the extent of absorption will be less, and this is because physics option do not has any is not associated with any barrier or the activation barrier. That is why this reaction is very easily reversible. So an increase in pressure, as we see these things we have seen. However, chemical absorption is usually irreversible, and why it is usually irreversible? Because each process involves an is associated with the barrier. Even the forward reaction is associated with the barrier, and so the reverse reaction is also associated with the barrier. And as we know, this process is exothermic, so the reverse process will have a higher activation barrier, and that is why as we, the, this processes are usually reversible. And if you remember that graph, if exothermic energy profile, if the exothermic reaction, this is reactant initially, and this is the product. So this was the barrier in the forward direction, and this was the barrier in the reverse direction. So barrier height or the activation energy increases in the reverse direction if the process is an exothermic process, and that is why, because of that, since chemisorption is also an exothermic process, this reverse process is irreversible, or this reaction, the chemisorption is irreversible usually. Physisorption is associated with low enthalpy of adsorption, and why it is low enthalpy of adsorption? This is because this physisorption happens only because of the weak van der Waals interactions, and so this is associated with the energy only in the order of 20 to 40 kilojoule per mole, and this is an exothermic process. So by this much amount, this kilojoule per mole energy will be released. And the chemisorption we also know it's exothermic, and but it is the enthalpy of absorption is very high, and it is ranges between 80 to 240 kilojoule per mole. So it is in the order of around 200 kilojoule per mole. Physisorption is a multi-layer in the physics of some multi-molecular layer of adsorbate are formed on the surface, and this is what we see. Even the gas surface, on the adsorbate, there will be interaction between adsorbate and adsorbate, and two adsorbates can have interaction. So multi-layer formation, molecular layer may of the adsorbate may formed on the surfaces, and that is why this thing liquefaction of gases, this kind of things, easily liquefiable gases are more adsorbed on the surfaces. This is because those gas molecules will have also between these gas molecules there is a higher interaction between those molecules, so multi-layer formation may happen. However, in the chemisorption, only monolayer are formed because chemisorption will happen only when the surface atoms of at the surfaces of the solid make a chemical bond with the adsorbate. And since once the chemical one layer is formed, all the adsorbate occupy all the activated atoms at the surfaces of the solid. Now there is no atom that is left even beyond that, so no further chemisorption will take place. So only monolayer formation or monomolecular layer formation happens in the case of chemisorption, because only once the monomolecular layer formation happens, all the surfaces of the solid will be saturated, and saturated because the atoms that were activated which has potential to form chemical bonds are now saturated. There is no vacancy for them, and so no further molecules will come, so the second layer formation will not happen. However, in the case of physical interaction or physisorption, even the gas molecule which got absorbed by the surface, now that molecule can have big interactions or van der Waals interaction with the molecules, gas molecules, which was in the gaseous phase. So that interaction will still be there. Those molecules will come in contact at the surfaces. So the multi-molecular layer formation can happen in the case of physisorption. So physisorption does not require appreciable energy of activation. So this thing one, it does not require appreciable energy of activation. Physisorption, because of the physisorption, we see chemical bonds also get affected to a very small extent. So it is associated with some barrier, but those barriers are not appreciable, they are not significant, they are almost negligible. So physisorption does not require appreciable energy of activation, they are almost negligible, they are almost barrierless. However, chemisorption requires high energy of activation in certain cases, and in certain cases it is very high, in certain cases it may be surpassable at room temperature, but it requires a significant barrier. So chemisorption requires a significant barrier. So porous substances, the physics of some porous substances are better adsorbents. And why they are better adsorbents in the case of physics of some? Because porous substances have higher surface area, and also the finely divided particles are better adsorbents because again the surface area increase. Yes. So the better adsorbents, why porous substances or the finely divided particles are better adsorbents? They because an increased surface area promotes adsorption in this case, and the same thing happens in the case of chemisorption as well, because the surface area of adsorbent increase in the surface area of adsorbent also increases the chemisorption, because more and the more activated atoms are now available on the surfaces, and so the extent of chemisorption will also increase. And the physisorption is favored by low temperature. So low temperature is favorable for adsorption, physisorption, and why it is favorable for physisorption? Because of it, even at the low temperatures, the interaction energy between gas molecules will be the van der Waals interactions will be there. However, at lower temperature, the entropy there will be decrease, and because of the decrease in entropy at lower temperature, but the interaction energy is still there, the enthalpy, so the physisorption will be more at lower temperature. In higher temperature, usually entropy increases, and so that physisorption is actually uh, negatively affected by increase in temperature. So it decreases, physisorption decreases with increase of temperature, because the absorption energy, the enthalpy of absorption will not increase with the temperature, but entropy will increase. So gas molecules, the randomness will increase, their degree of freedom will increase. That not the freedom will increase, one can say, and so the at higher temperature, physisorption will be negatively affected, means it will decrease. However, chemisorption, in the case of chemisorption, this chemi-absorption is actually favorably affected by temperature because chemi-absorption requires activation barrier. Those activation barriers will now be surpassed at higher temperature, that can easily be surpassed at higher temperature. So more and more molecules will now chemi-absorb at the surfaces of the solid. And so chemi-absorption will increase with increasing temperature. And now let's next we study about adsorption isotherm and adsorption isotherm. So few terms only we will study, and then fluidic adsorption isotherm we'll see from our next class. So what we see adsorption isotherm. Isotherm, isotherm means at a particular temperature when you draw a graph, and that graph must represent the adsorption of the gas molecule. So the variation in the amount of gas adsorbed by the adsorbent with pressure at constant temperature. That means that is why this is called isotherm. At constant temperature can be expressed by means of a curve termed as adsorption isotherm, and that curve is called adsorption isotherm. What is that curve looks like, that we will see in great detail in our next class. This is one type of adsorption isotherm. This is also adsorption isotherm. This is another adsorption isotherm, and this adsorption isotherms are at different temperatures. You can see. So, what is the variation in the amount of gas absorbed by the adsorbent with pressure at constant temperature can be expressed by means of a curve, which is termed as absorption isotherm. So, at the constant temperature, when the amount of gas that is absorbed, when it is plotted against pressure, we see a curve, and that curve is called the absorption isotherm. And thus, adsorption isotherm can also be expressed in terms of a mathematical equation, because we have certain graph, and every graph that we know, we can get the equation for that graph. So the adsorption isotherm is also associated, can also be expressed in terms of the mathematical equation, and this mathematical equation describes the relationship between pressure of the gaseous adsorbent, and that is why the pressure we have seen, pressure of the gaseous adsorbent and the extent of adsorption at any fixed temperature. So the extent of adsorption, this term I am using, I have used many times here, I have also used, and this is at the fixed temperature for the isotherm, that curve. So what is the extent of adsorption? The extent of adsorption, we must understand what does it mean and how it is defined. The extent of adsorption is expressed as mass of the adsorbent adsorbed on 1 unit mass of the adsorbent. So the mass of adsorbent adsorbed per unit mass of adsorbent is called the extent of adsorption. So suppose x gram of an adsorbent is adsorbed, and what mass of adsorbent we have used, suppose m gram mass of adsorbent we have used. So per unit mass of adsorbent, how many grams of the mass, what mass of adsorbent will be adsorbed? It will be x divided by m, because we have to get the extent or mass of adsorbent per gram of the adsorbent. And so x by m and the unit both can have the same unit, and the x by m, so this will be a unitless quantity, and this we define as extent of adsorption. So per unit mass of adsorbent, whatever the mass of adsorbent that is adsorbed is called extent of adsorption. And with this, I'll stop today's lecture, and we'll see this fluidic adsorption isotherm and what is its importance and what are its implications. Those things we'll see in our next class, that will be on the next Sunday.